What's up, everybody, and welcome back. So today we're going to be going through a little bit of the history of the nitrogen manufacturing process, why it was initially created to begin with, what inspired that movement, and what might have happened had it never taken place. So grab your favorite beverage, sit down and buckle up. We're going to go for a little bit of a journey. Let's do it.
What's up, everybody?
So in order to understand this and where I'm going to be going in this video, we need to do a little bit of a history lesson first and just go back in time a little ways. We're not going back to the cavemen like we did in the crabgrass video. And if you haven't watched that video, you should. It's really fun. So first of all, let's just go back to Cato the Elder real quick, who wrote the first book on agriculture, talking about crop rotation, talking about nutrient management, talking about the best ways to even manage your livestock, what a farm can produce, what a family should expect out of it. Lots and lots of information was documented at that time. Now, a lot of those particular practices as far as tillage and rotation and those types of things have been kept in even up through modern times and haven't really changed a whole lot. Perhaps we could get into the tillage aspect in a later video, but not for this one. So as humanity expanded and civilizations grew and cities grew and populations grew, there became more of a taxing on the crops that were being produced in order to make sure that everybody was being fed. We needed to get more out of those farms. So there were a couple of things happening, and they continue to happen to this day, which is just sort of the struggle of modern farming, is populations increase, start taking up some of the land mass that was dedicated to farmland, and therefore what's remaining of the farmland has to produce at an even higher rate. So this has been going on for millennia. This is nothing new, it's just the way it's always been. So now if we jump forward a little ways and we reference Justus von Liebig, who's somebody I have done teachings on about Liebig's barrel and the law of minimums, he was really starting to look at what was always going to be in the least amount of supply and what should be supplemented into the soil in order to have the best crops. That was really what his contribution was figuring out the law of minimums. Now it's been pretty much determined that nitrogen is almost always in the most limited supply, and that is why it is supplied the most to crops. Even though it is only part of an entire nutritional program, that is the one that seems to be missing the most. So adding nitrogenous materials to crops was nothing new, but it was typically used with animal waste, compost, manures, plant matter, all of that kind of thing were put down and put back into the soil in order to have at least some level of nitrogen down in the ground. It was nowhere near the amount that could be supplied with a chemical fertilizer, but it was something that was enough to give a yield to the crops that people needed. So if we move forward a little bit more, we can talk about saltpeter. Now, saltpeter was traditionally used in the making of munitions, and so it was highly sought after all around the world, and there were massive deposits down in Chile which were getting mined out at a very, very high rate. And that was eventually going to deplete. So this started to become more of a problem because it was being used both for munitions manufacturing as well as for putting down on crops, because there was definitely a huge noted increase in yield on crops when saltpeter was applied. So this made this whole area kind of a hot point of contention as ships came in and out, gathering up that saltpeter and truly depleting the supplies. So we can pause for a minute and talk about just the supplies of certain materials that are around the world. And there's two that are part of the big three that were and are still somewhat in limited supply naturally. Number one would be that saltpeter is something that could eventually run out if it was only used for crops. And the second is phosphorus. Now, we are running on a limited supply of phosphorus around the world, and as we go on, there will have to be different ways to make up for that nutrient over time. It is likely that we will come to a point in our future where we do see more green waste style recycling in order to make up for some of the phosphorus deficiencies that could eventually affect crop growth in the future. So let's jump forward just a little bit. In 1898, Sir William Crookes was made president of the British Association for the Advancement of Science. In his inaugural address, Sir William Crookes talked about an oncoming disaster, which was going to be famine and starvation due to the overwhelming population of the world increasing at a high rate and the lack of farmland. He called upon scientists to truly dedicate their time and their energy into finding out how to capture atmospheric nitrogen and create fertilizer in order to not have the world starving by 1930. The list of discoveries that Sir William Crookes gave to the world was pretty fantastic, but one of his later years was the discovery of the gas argon, along with a couple of other scientists. So he was working with atmospheric gases at that point, and as many of you probably know, the atmosphere that surrounds us is almost 80% nitrogen. That nitrogen isn't actually available to plants in its atmospheric form. It's in a triple bond, and that requires a splitting plus an additive of hydrogen in order to get ammonia. So we go from an N2, which is the gas in the air, to an NH3, which is ammonia, in order for it to be fertilizer. Well, let's talk about that process here for a second. There are really only a few ways to actually get usable nitrogen out of the air, and the Earth does a pretty good job of that currently. So let's take a look at a couple of different ways that that chemical reaction can actually happen. So we're going to talk about the biological process of it first. Now, just to give you an idea of the grand scale of the way that the Earth works, around 200 million tons is converted from atmosphere down into plant available nitrogen around the world annually. That's through multiple different biological processes. Some of it is even by the ocean. Obviously, as nitrogen is important as a building block for protein for everything living on the planet, the Earth has a way to create that on its own. Now, we can go ahead and take that number and match it up to what's currently happening in manufacturing. We have around 200 million tons that's being produced through biological processes, and now almost the same amount is being produced by manufacturing processes today. So one of the ways that was first initially looked at creating ammonia was to do it in the same way that we see nature doing it with lightning. The electrical charge has the ability to fix nitrogen from the atmosphere, but that rate is actually pretty low. Only around 7 million tons out of those entire processes that I mentioned earlier is contributed to lightning itself. But initially, that was what was thought was going to be the best way to do this. So at the late 19th century, early 20th century, that was one of the first ways that was experimented with getting nitrogen from the air into a form that could be used by crops. So this actually involved compressing atmospheric gas and passing high energy through electrodes, and it just didn't really yield much, and the amount of energy it took to create that wasn't going to be worthwhile. So now we move into this Haber-Bosch process that began to happen later. Now, it's called the Haber-Bosch because there were two different scientists that were working on it. Fritz Haber, who was the initial person who designed the sort of Haber machine, as it were, or the technique, and then Carl Bosch, who worked for BASF, who was the engineer that actually helped to design the entire industrial scale of this particular nitrogen fixing process. So this whole thing worked sort of as a big pump. Air was brought in, it was put into big tanks, it was heated until the nitrogen was split apart, steam was introduced so that the hydrogen can be there, and then the ammonia sort of formed into a gas, and then eventually, as it cooled down, was settled into tanks. This obviously was a huge breakthrough, and it was actually pretty easy to put out onto an industrial scale. Now I'm going to skip the part about the catalysts that were used and how they kind of came around to this. That's something you can research a little bit later. The point is, now we were making nitrogen, and that was huge. There are a couple of negatives that happened because of this entire process. As the world wars began to take place and Hitler came to power, it was estimated that Hitler would have run out of munitions in about 3 months had this process not been invented. It was this whole process of being able to create nitrogen and use it for munitions that actually kept that war going for a while. Again, this is another topic that could be gone into at a later date, but if you want to find out more about that, read The Alchemy of Air. It is a wonderful book, and it will open your mind to a lot of this conversation. So now at the end of the war, there is fertilizer aplenty, and these factories can go up pretty much everywhere. The process of building them wasn't even all of that complicated, and now all around the world there are nitrogen plants all over the place. Here in the United States, we have about 36 plants in roughly 18 states, but the bulk of it is all coming from the Gulf states. So Louisiana and Texas have a significant amount of nitrogen production capacity here in the United States. But really over the past year, the plants were only running at about 90%, with 2 of them actually shut down. So we weren't even running at full capacity here in the US. But again, a majority of that, 80% of that production is going to fertilizers. Okay, so that was sort of a flyover history of everything. Now it's time to sort of back up and take a look at maybe what could have happened had things been a little different. So the first thing is, food production was the biggest and most important part of why this whole process took place. It was to feed the population. Now, when this concern came up in the late 19th century, there were around 1.8 billion people on the planet. Today, we have 6 billion more people than that, and it's only been about 120 years. That number is increasing very rapidly. The takeaway on this, I think, is really the most interesting. 2 out of 5 of us, 2 in 5, 40% of us owe our lives to that particular process because of the food that has been produced, and how we've been able to survive as humans is because of that fertility process. If you really think about it, had the process never been invented and never been created, it was almost equivalent to Thanos' snap. Even without a supervillain, you could see how detrimental that would have been to the human population. But that is something to think about, is what would the world look like today? It's currently estimated that 51% of the nitrogen that's in our bodies right now actually came from factories. But what would that really look like to our crops and to the way that production was actually being made? Well, obviously population wouldn't have exploded like it has over the last 100 years. You see things in these cities that have just gotten bigger and bigger and bigger over the last 100 years at an insane population increase. Well, that is because of the abundance of food, and it truly is an abundance of food. Now, it's still estimated that about 20% of the world is in some level of famine. 20% of the world is underfed. On the flip side of that, in the United States, 20% of the solid waste in landfills is from food waste, just brushed away into the garbage and shipped off in trucks. Again, this is something for a later video. I want to equate this into lawns. So prior to the prevalence and the availability of nitrogen, things were done a little bit different. It was done through nutrient cycling, through clippings of grass, through animal waste, through manures, through composting, through putting back what was being taken off the ground back down onto the land. Now, that didn't mean that we would actually have the landscapes that we have today. There's a few things that really need to be taken into consideration here, because let's assume that we did not have this nitrogen production available. That didn't happen. But everything else, as far as the technology, the seed breeding, the changes in genetics over the time with plants. Now that's crops, but it also includes turf. Now we have all of these different breeders out there that are creating different turf types off of a main dominant species in order to give it characteristics that will allow it to function in more harsh environments, whether that be drought, whether that be extreme heat, whether that be extreme cold, growth rate changes on the turf itself. All of these things are being done and designed and changed and manipulated really on a daily basis. If we go back into the 1930s, Penn State was really the first school to offer a turf program, and the original professor to that came from the crop and forage side. So a lot of what he was looking at when he brought in information about turf science came from the crop grasses side of things, which is where a lot of our information became established. So because so many cereal grains and grasses are in the same family of Poaceae, this is something that kind of made sense to bring the information from one side into the other. So the agronomy of growing corn and forage crops was brought into the turf side. But again, let's look at it from the fact that we don't have nitrogen being produced. Well, there's a couple of things that probably would have happened. So first of all, some of our cultural practices probably would have changed. Now, our feeding schedules might have looked a little bit different. I would imagine that a lot of things would have been done in the same way as agriculture, where more manures and green waste were used, and they were maybe spread across your entire lawn and landscape once a year, likely in the fall, maybe early in the spring, and that material would break down and slowly feed throughout the course of the season. Now, that could obviously lead to a couple of different things, because one thing that we do know is a thicker, denser canopy of turf is going to keep more weeds out. It's likely, however, that there wouldn't be as much care or need to care for lawns in the way that we see it today. It actually would have probably remained somewhat of this sort of elitist look at things, because we didn't have a way to easily manage, easily feed, and easily take care of green space. If we weren't able to just go down and buy a bag of fertilizer and lay it down, it would have actually taken a way more agronomic approach in order to make things green and beautiful in the way that we see them now. Now, I guess one thing is, you probably would have a lot more green space if there were only 60% of the houses around than there are today. But that is a little bit of a scary thought, to think that there is such a major change in how many of us are in existence today because of that one invention. So had ammonia not been able to be captured out of the atmosphere, and that manufacturing process had not been invented, we would be back to what we're calling today more organic practices, which, again, organic practices would have just been considered fertilizing prior to this point. So it is something to really consider when you're taking a look at your overall program and why that's important. One of the big things that has changed, that has been noted, because of the ability to produce greater crops or thicker grass or faster growing plants, or however you want to look at it, is it does tax a little bit more on the rest of the soil system as a whole. And because we aren't actually giving that green waste back, because we aren't actually doing a lot of this nutrient cycling, we're missing out on that particular piece. We're only giving it the nitrogen to sort of feed and give the gas without replacing some of the other items that might get chewed up along the process. So these are the considerations for your program, and this is where I think that we have to sort of broaden our scope in the way that we're doing things. Now, I've mentioned this in so many different videos. Grass, the way that we're growing it, is not a crop. It doesn't require the same amount of nitrogen that corn does. And for a lot of people, that's the number that they're feeding at. If you consider for a moment that you go out there and you place down on your ground, say 1 pound of nitrogen per 1,000 square feet on average on every application that you do, or let's say even up to 6 times a year, that's kind of a lot, and there's a lot of turf grass that says, yeah, I can take that. There's so much more behind it to get to that number and why it does and doesn't work. Some of it has to do with soil types, some of it has to do with water and precipitation, some of it has to do with washout, some of it has to do with volatilization. There's all of these different things that get calculated into giving that number to your turf grass. But if I take that number and I multiply it out over the course of an acre, and I say I've got, for the sake of this argument, let's say 44,000 square feet instead of 43,560. We can do kind of easier math like that. But at 4 pounds per 1,000 square feet, I'm putting out 176 pounds of nitrogen per acre. That's enough to grow 176 bushels of corn. If I'm going to 6, well, now I'm growing 250 bushels of corn. I can really push that number up. But this is just on a lawn, something that's there to look pretty. That's pretty much what its function is for us as homeowners, is just beautification and honestly a little bit of satisfaction. So really what we start to come down to is, what is it that we really need? What do we need to be putting out there, and what is going to be the most important thing for us going forward? As we've increased nitrogen levels, as we put more down onto the ground, as we push growth further, we tend to bag more, we tend to haul away clippings, we tend to not recycle what we're doing. We're also stunting some of the root development because we're not allowing that food to slowly work its way down through the system, it actually stays more close to the surface, and that actually causes a shallow rooting system, which over time will end up depleting the quality of the soil as well as cause more stretches throughout the season, which in turn requires more nitrogen to push it out further. So it's sort of a snowball effect that needs to be watched and slowed down. If we take a look at it from a little bit of a different perspective, when we don't go through those first initial force surges and force growth phases, we can start to slow down how that grass is going to grow over the course of the season. It still is going to be there to survive and thrive and photosynthesize and do everything that it needs to do, even with less gas given to it. We're basically just slowing down a metabolistic rate at that point to where the grass can't surge like crazy by lowering the amounts of N that we're going to give to it. If, on the other hand, your goal was to actually grow seed, or if it was to grow the crop from seed and harvest it, you would need to push more nitrogen to it, but once it's established, you don't. And that's where we get a little bit sideways, because a lot of this concept of how much we're feeding to the grass comes from the establishment and comes from the farming of that grass, not from the ongoing maintenance of that turf. A good portion of these rates that have been put out there are to get grass to market, or if it's an extremely high traffic zone, like sports fields or golf courses or parks or something like that, where the grass is constantly getting trampled on and it needs to have more energy to recover, would be another great example of a reason to feed a little bit heavier into that system. But for the most part, with the way our home lawns are, pushing and pushing and pushing basically just means going out and pushing a mower and pushing a mower and pushing a mower and not actually getting a further overall quality of turf, just a faster growing turf. So this is where I'm going to sign off. I thought it might be nice to have everybody just sort of think and speculate on about how this last 100 years has actually been, some of the advancements that have happened and what we now have to thank for those advancements. And then also to take a minute and speculate on what it might have looked like without it. What sort of world would we be living in? But that's it. I hope you guys enjoyed it. I'll talk to you guys real soon. See ya.